Let's talk a little bit about properties of vector operations. Now, these are probably things you could have guessed already, so I'm not going to spend a ton of time on them, but I'm going to walk you through each one of them. The first one is, again, something you probably could have guessed, is that the order of addition doesn't matter. U plus V is equal to V plus U, because remember, we're just adding the components, and addition is commutative for general real numbers, so no problem. The second one is that it doesn't matter which order you add vectors in. And again, you probably could have figured that out from property one, which is that if you have three vectors, it doesn't matter if you add the first two or if you add the last two. If you're going to add them all together, it doesn't matter. You just add them however is convenient, which is nice. The third one is that if you add the zero vector to any vector, you get the same vector back. That makes sense. You're just adding 0 to every component, stays the same component. This one isn't really that tricky, but it might seem originally, is that if you add the additive inverse, or you add the negated version, or the negative, whatever you want to call it, if you add the negative version of a vector to itself, you get the 0 vector. That kind of makes sense, right? If you think about that in terms of distance, if you go somewhere and then you come back, we haven't gone anywhere. That's really the idea behind this. Number 5 is this idea that if you have two scalars multiplied by the vector, it doesn't matter the order that you multiply. You can multiply the scalar times the vector and then scale that again, or you can multiply the two scalars together before you ever multiply to the vector. This is usually the more convenient one, because this means, if this is let's say it's a 10D vector, right? Then you have to perform 10 multiplications, and then you have to perform 10 more multiplications. That's 20, versus one multiplication and 10, that's just 11. Number 6, if you have two scalars added together, multiplied by a vector, you can split up the scalars. That's sometimes useful. Like, think if this was a whole number and this was like a square root, like some sort of radical, then it might make sense to have a nice clean vector for the whole number and then have that nasty radical one over here. So you have the kind of a similar situation, except instead of with scalars, you now have added vectors. So it might be more convenient to add two vectors together and then scale it, or it might make more sense to scale it individually. Again, really, that's when you come down and look at the components. This is all just preference. It's really just things that are convenient. A lot of mathematics is about knowing the properties, so you know how to break things apart in a very specific way, and then you can kind of assemble them back together in a convenient way that helps you wrap your head around it. And finally, number 8 is really just a consequence we probably already knew, is that 1 times a vector is itself, and 0 times a vector is the 0 vector. And that's really a consequence of that scalar multiplication. 1 times everything is just everything that was there. 0 times all your components, well, 0 for each component, so it's got to be the 0 vector. And that's really just the properties of vector operations. Pretty simple, straightforward.